A recent study shows a connection between a genetic mutation and bone density. A company created a test and claims a 96% accuracy rate in the general population. 1 in 600 actually carry this mutation. Use a population of 60,000 to construct a table. So when you think about creating a table for false positives and false negatives, right, we think of, at least this is how I think of it, this top spot are those that actually have the mutation. These people do not have the mutation, and we would call this our total. Then in this first line, these people will test positive, these people will test negative, and over here is our total. You'll notice these are not equal, and that's okay. So our instructions are to use 60,000 to construct the table. So we have a population of 60,000. Well, we know that 1 in 600 actually carry the mutation. So if we would say, well, 1 out of 600 have it, so how many out of 60,000? And if you solve this proportion, 600x equals 60,000, and so x equals 100. So 100 actually would have the mutation. So 60,000 minus the 100 would give me 59,900 that do not have the mutation. So then when we go back and we think about those that will test positive, well, it's a 96% accurate rate. So again, remember, if you have the mutation, you would expect to test positive. So this spot would be 96% times the 100 people who actually have it. So when I take 0.96 times 100, I end up with 96 out of 100 will test positive. The other 4 who have the mutation would unfortunately test negative. Now the same thing works for those that do not have it. If you do not have the mutation, you would expect to test negative. So the 96% accuracy rate will be multiplied by the 59,900. So when I multiply the 96% times 59.9, I end up with 57,504. And working backwards, if I take my total 59.9 and subtract my 57,504, that will give me a total over here of 2,396. And now I add vertically to get my totals, 2,492 and 57,508. Now with my table, I can answer some questions about it. So we will answer 2 questions to go with this problem. First one, what is the likelihood that someone does not carry the mutation if they test positive? So we are now only looking at the test positive column. So we know we've got 96, and this is the ones that have it. Do not have it is 2396, and our total was 2492. We're focusing on this column because it says if they test positive. So that tells me this is what matters. So here's my total. So I know my denominator is going to be 2492, and my numerator is they do not carry the mutation. Well, that's 2396. When I turn that into a decimal, I get 0.9615. So you've got a 96.15% chance of not having the mutation if you test positive. That's really, really small. You would obviously want, well, I shouldn't say obviously, I would want a second test because to see whether or not I really have it. If you test positive twice in a row, that might be a little bit more telling. Let's also go with number 2, the likelihood that someone does have the mutation if they test negative. So now we're focusing on the test negative column because if they test negative. So we know that 4 people will test negative if they have it. Those that do not have it is 57,504 for a total of 57,508. So when I look at this, my denominator is 57,508. That's the total number of people who tested negative. So what's the likelihood that they have the mutation? 4 out of 57,508, and as a decimal, it's 0.00006956. That is super small, super small. So if you test negative, it is highly unlikely that you have the mutation.